Section 2.7 is on page 76, talks about numerical approximation and the Euler's method. So, dy dt equal f of ty. What we're doing here, we're taking this function and setting it to be the derivative with initial conditions saying when t equal 0, y equals 0, or t sub 0 equals s sub 0, depending on the value, of course. Now what we're trying to do, we're trying to approximate a function. Let's say this is y equal, and this look like some phi of t, function of time, doesn't matter what it is. And this is how it works. We need to use an equation of a line, and if you remember how this works, equation of a line is y minus y1 equal m into x minus x1. This is the point slope equation of a line, which x1, y1 is the point and m is the slope. So what we do, we take this interval, we say let that be t sub 0, t sub 1, t sub 2, t sub 3, and the list goes on, t sub 4. And what we do, we take t sub 1, t sub 0, y sub 0. That's the initial point given. That's this point right there. And we say if you take that point, you're looking at y minus y naught equal m. And in this case, do remember what we're going to use as a derivative. We're going to say that is m into x minus x naught. And if I really fill in the blanks, right? If I really come in and say, well, let's see. I'm going to go from this, and I'm going to figure out the slope of the tangent at that point. It's a line. But I'm going to stop at t sub 1. And now, this point right here is going to be t sub 1. And if I plug that in, calling that t sub 1 some y sub 1, I'm going to really plug in and say y sub 1 minus y sub 0 equal, and m, I already know it is going to be at this point f of t sub 0 y sub 0, because the slope is dependent on that piece, times t sub 1 minus t sub 0. And that's going from this point to this point. So here, if I solve for y sub 1, that would be y sub 0 plus f of t sub 0 y sub 0 into t sub 1 minus t sub 0. And if I go in and I do this again, I say, okay, you know what now? Let's go to t sub 1 y sub 1. Y minus y sub 1 equal m into, I'm so used to x, into t minus t sub 1. What I'm doing now, I'm actually finding the slope of the tangent is going to be more flat than the initial. We know how that works, right? That's the slope of the tangent, that's the slope of the tangent. It depends on the curve. And here, I'm going to do the same thing. I'm going to say, you know what? If I call this point right here t sub 2, y sub 2, then I'm going to have y sub 2 minus y sub 1 equal, and m in this case is going to be the slope at this point. That's going to be f of t1, y1 times t sub 2 minus t sub 1. And if I solve this for y sub 2, that would be y sub 1 plus f of t sub 1 y sub 1 into t sub 2 minus t sub 1. So, what I get out of this is that y sub 1 equal y sub 0 plus f of t sub 0 y sub 0 times t sub 1 minus t sub 2. If I look at y sub 2, that is y sub 1 plus f of t sub 1 y sub 1 times t sub 2 minus t sub 1. If the trend goes on, I will get y sub n to equal, and notice whatever this is 1, I don't want to say n minus 1, let's say y sub n plus 1 equal y sub n plus, and whatever this is 1 less, t sub n, y sub n, t sub n minus t sub n plus 1 minus t sub n. Right? And if I really look at this, I could say at any given point that's going to equal y sub n plus f of t sub n y sub n times, the book refers to this step, we called it delta x back in the days. The book refers to this as h, which is the same distance, h, that's sort of like our delta x, right? And that would be the formula for finding y sub n plus 1. This is the derivative, it's right there. And this y is just the previous y before that. I want to look at a problem. I want to start with problem number 2, and we're going to focus only on parts A and D. So they give us t, 0.1, 0.2, 0.3, 0.4. And this is the Euler formula, of course, the famous Euler. You're going to know a lot about this guy. So in part A, what we want to do, we want to use the formula to approximate. And in part B, we would like to actually find the solution, and we'll talk about that when we get there. For now, on page 83, I'm looking at number 2. So I have y sub n plus 1 equal y sub n plus f of t sub n y sub n times h, and h is actually right there. In this case, they specified h to be 0.1 in each of those. So, initially, I have the point 0, 1. That's t sub 0, y sub 0. If I look at y sub 1, that is y sub 0 plus f of t sub 0, y sub 0 times h. And if I plug in what I know, y sub 0 is 1, plus f of t sub 0 is 0, y sub 0 is 1, and 0.1 is the h. This is what I'm going to call this. That is f of x, y. So this is going to be actually 1 plus. If I throw a 0 in for x, there is no x, this depends only on y. That's going to be 2 times 1 minus 1 times 0.1, and that turns out to be a 1.1. If I go for y sub 2, that is y sub 1 plus f of t sub 1, y sub 1 times h. That is, y sub 1 now is already figured out to be 1.1. Plus f of t sub 1, well, t sub 1 now has just went up to 0.1 because that's where I'm going. I'm moving in 0.1 steps. 1.1 for y times 0.1. So this is going to be 1.1 plus, and if I plug this in there, I will get 2 times 1.1 minus 1, and I'm going to multiply that by 0.1. Throw this in my calculator, that's 1.22. And if I go for y sub 3, that's going to be y sub 2 plus f of t sub 2 y sub 2 times h. Well, that's 1.22 plus f of t sub 2 is 0. 0.2, 1.22 times 0.1, and that will be 1.22 plus, and again if I plug in, there's no t in there, there's just y, so that's going to be 2 times 1.22 minus 1 times 0.1. Throw this in my calculator, I'll get a 1.364. And one more, if I find y sub 4, that's y sub 3 plus f of t sub 3 y sub 3 times h. That is 1.364 plus f of 0.3. 1.364 times 0.1. That is 1.364 times a plus 2 times 1.364 minus 1 times 0.1. And this turns out to be a 1.5368. So those are my approximations. If you notice what they want us to do in part D, they say find the solution, plug in the values, and compare those between A and D. Well, let's see. If I'm given this equation, this is a separable equation. So if I take dy dx, or I could say actually y prime minus 2y equal negative 1, the u factor is e to the integral of negative 2 dt, that is e to the negative 2t. So if I multiply this by u, this will be y prime e to the negative 2t minus 2e to the negative 2ty equal negative e to the negative 2t. This would be a derivative of y e to the negative 2t equaling negative e to the negative 2t. If I integrate with respect to t, I will get y e to the negative 2t equaling e to the negative 2t divided by 2 plus c, and y would equal 1/2 plus c e to the 2t. Now y of 0 equals 1/2 plus c, and that is a 1. So c equals 1/2. So my solution is y equal 1/2 plus 1/2 e to the 2t. This is the exact answer. The solution is y equal, the book likes phi, but it's the same thing, 1/2 plus 1/2 e to the 2t. This is the approximation using Euler's. So if I go by Euler's, Euler got 1 for 0, then got a 1.22, no, 1.1 was the next one, right? 1.1, 1.22, 1.364, and 1.5368. Now, if I take 0 and I plug in 0 right there, right, I will get a 1. That's not a problem. If I put 0.1 in there, this is what I'll get, 0.2. So you notice 1.1 is accurate to 1 decimals. 1.2 is accurate to 1 decimal. 1.4, if you round this, that's accurate to 1 decimal. And 1.6 is slightly off. But that's a very good approximation instead of finding the solution. There is a whole math class on this. That's you take at Cal Poly if you ever go there, but I'm sure you take it at other schools as well. We want to do another problem, and the same deal. We want to do number 4, and number 4 has the initial point being 0, 0. This is t sub 0, y sub 0. So here, if I go ahead and say, you know what, I know that y sub n plus 1 is y sub n plus f of t sub n y sub n times h. And the same deal, so if I say y sub 1 is y sub 0 plus f of t sub 0 y sub 0 times h, just like calculus, if you see a trig function, make sure you are in radian mode. Otherwise, it doesn't work. Radian mode. And that's true all throughout. So this will be y sub 0 is 0 plus f of t sub 0 is 0, y sub 0 is 0 times 0.1. Well, that's going to be 0 plus, if I plug this in for t and y, that is 3 the cosine of 0 minus 2 times 0 times 0.1. This is 3 times 0.1. That turns out to be a simple 0.3. So that's my first value for y. If I go for y sub 2, that is y sub 1 plus f of t sub 1 y sub 1 times h. That is 0.3 plus f of t now is 0.1, and I'm going for a y 0.3 times 0.1. If I plug this in, 0.3 plus, if I throw these values in, that is 3 times the cosine of 0.1 minus 2 times 0.3, all multiplied by 0.1. And if I throw this in my calculator, I will get that number. If I go for y sub 3, that is y sub 2 plus f of t sub 2 y sub 2. Well, this is a 0.538501. I'm going to choose to take it to 6 decimals. Plus f of x is 0.2 now, and y is 0.538501 times 0.1. And this will be 0.538501 plus f of 2, that's 3 the cosine of 0.2 minus 2 times y, 0.538501, all multiplied by 0.1. Y sub 3 turns out to be a 0.72418. And if I go by and I do the last approximation, okay, this is giving me a hard time. If I go for y sub 4, that's going to be y sub 3. Y sub 3 is 0.72482 plus f of 0.3, 0.72482 times 0.1. That will be a 0.72482 plus f of, and that's going to be 3 times the cosine of 0.3 minus 2 times 0.72482, all multiplied by 0.1. And if I plug this in my calculator, y sub 4 will turn out to be, I shouldn't have moved that, huh? There it is. And in part D, obviously they want us to solve. I copied these down, so this is part D. Well, this is, again, if you really think about it, this would be y prime minus 3 minus 2 plus 2y equals 3 the cosine of t. The u factor is e to the integral of 2 dt, that is e to the 2t. Multiply this by u, this will be e to the 2t times y prime plus 2 e to the 2ty equal 3 e to the 2t cosine of t. This becomes a derivative of a product rule, basically of y e to the 2t. You integrate with respect to t, and you will get y e to the 2t equaling, and if I break this up right here, I will get this to be 3/5 e to the 2t times twice the cosine of t plus sine of t plus c. And y would simply equal 3/5 times twice the cosine of t plus sine of t plus c e to the negative 2t. I need to find the initial condition, so that's where this comes in. Y of 0 will equal 3/5 times twice cosine of 0 is 1 plus c, and that equals a 0. So c will equal negative 6/5, and y will actually equal 3/5 into twice the cosine of t plus sine of t minus 6/5 e to the negative 2t, and that's what's going to go here. Just copy that down here. This is h, and the approximate I already got. The approximate we got to be 0 initially, it's right there. I got a 0.3 the first time, 0.5385, 0.7248, and 0.86644. If I plug in t equals 0 in there, I would simply get 0. If I put a 0 in there, I'll get 6/5 minus 6/5, which is 0. If I plug in 0.1 for t, plug that in my calculator, I notice if you round this, you get 0.3, and if you round this, you get 0.5, if you round this, you get 0.7, and if you round this, you get 0.8. So the approximation is very close, and you're going to do then the homework, numbers 1 and 3, and you're going to do just parts A and D for both. A and D on both. All right.